This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everyone. Hello. Take a seat quickly. All right, so today will be the second lecture about materials and systems. So we've seen concrete last week, and in combination with foundation systems. Today we're going to look at timber, because we know that since you have completed, or you've drafted at least, the first two stages of the second assignment, you are going to deal in tomorrow's tutorial with the building frame. So most of you will have to deal with stud walls and stuff like that. So that's why timber is particularly relevant for you in this week. So what we'll cover today, as usual, when we deal with materials, so for the remaining 3 lectures, including this one, we'll always look first at the material properties. So we'll look at the wood properties, manufacturing, defects, treatments, and all the things that you can add in your assignments as annotations and captions to images. Then we'll have a look at some composite products, because for instance they'll be relevant for joists or truss systems, and a little bit of just some basic notions of the structural and mechanical properties of timber, because you'll need to know that we are dealing with an orthotropic material and not an isotropic material, which would be easier to deal with. So the way the lecture is organized is that the first part will be assessed at the exam. So we'll formulate exam questions from the first part in particular, and not the second part, because we believe that what we're going to discuss in the second part of the lecture can be very well assessed through the assignments. So that's why we're going to discuss the difference between balloon frame and platform frame, or let's say the evolution of timber construction until platform framing. Then we're going to have a look in detail at the platform framing elements and components, connections, joints, openings, and in between I'm going to show you some previous students' work. So we're going to look at some assignments. How is the microphone volume? Is that okay, or it's a bit too low, too loud? Right, so the way the folder has been organized on the LMS follows the structure of last week. So there will be, this is a snapshot of the LMS as of today. So there is, you'll find the lecture slides here, and then some other resources up there. So within those 4 files, there are some exam questions, which I suggest you download and look at, and then you'll keep them there for the exam preparation after week 12. But then there are also some other resources that are particularly important for the development of your assignment. They're all available offline, but what we've done is mainly just to collect material that is openly available. We have decided to make a selection and just bring it here for you. The first important document you'll need to consider as the Bible for the next weeks is this Australian standard, the 1684.4, that's related to residential timber framing. In that you'll find everything: terminology, definitions, all the timber elements, connections, bracing. Everything is in there. I highly recommend you get a copy of these, even as a you keep it as a hard copy, because it's particularly important. You'll find most of the details you need. and all the instructions about spacing of the studs, the joist, everything is really in there. So we've been drawing information from this standard. And also, there's this book, Fundamentals of Building Construction, by Allen. It's not a book about timber, but there are at least 5 chapters, which I'm not asking you to read and study, just letting you know that the way we construct the lectures, we take information from books, online resources, and somehow we put them together to make a lecture like this one. So there are, in particular, 5 chapters that are relevant for you today. Chapter 3, 4, 5, 6, 7, which are related to timber in different ways, from structural applications to finishes, flooring, cladding. And there are also other 2 chapters, which I believe I forgot mentioning last week, but they're still relevant for the development of the second assignment. So foundations and site work and concrete construction. So that would be chapter 2 and chapter 13. As I said, I'm not asking you to go through this book because it's a big book. But I'm just saying you can browse it, and it's also available as an electronic resource. So in the case you need it for your assignments, it's always there for you. Now, let's start with wood properties. How many of you have already studied timber products in first year? How many of you already made models with timber products in year 1? 2 people? 3? Good. I was expecting a bit more. Anyway, this is how timber looks like when it's cut. So what happens is that trees, they generally grow vertically. And as they grow, they'll need to stand wind forces, and therefore they will also grow in the other direction. And this growth will develop 2 separate parts. So there is the hardwood, which is this dark brown here. It's made of inactive cells, all right? And then there is the sapwood, which is around. So the sapwood is made of these rays or rings which identify the age of the tree. So that part is made of active cells. And then there is the bark, that for instance is what we see of the tree, and that is dead. It's not part of the tree as a living organism, all right? So that's all you need to know for the moment. The 2 parts made of inactive cells and active cells. And as it grows, it will also expand. And these 2 things will make sure that the autotropic nature of this material will develop. So just to remind you some terms, stiffness, which is the resistance to deflection. Deflection when we talk about vertical deflection under a point load or a distributed load. Strength. Strength, it just means the amount of force that can be carried by a particular object of material before it breaks. And then the last one, which could be called toughness or better robustness, it's the ability to resist to the propagation of cracks or problems. So let's say there is a problem in the roof structure of this theater. So if that particular problem is, the structure is able to keep the problem locally and that doesn't propagate throughout the structure, we can say that the structure is robust enough. When a little small problem in the corner of the theater roof structure is spreading immediately throughout the structure and then that is going to collapse, we cannot say that we're talking about a very robust structure. Right? So that is the property of robustness. Now, there is another very important thing you need to know. The cellular structure of wood, it's not only non-homogeneous in the three different directions, it's also made of, it's a hollow structure. So it means there will be moisture inside. And you'll see in a moment why I'm mentioning that there is moisture inside, because we'll need to season the product before using it for structural purposes and also for cladding and flooring. You see here there are two percentages, 90% and 10%. Considering the way that the timber trunk grows, most of the fibers, or let's say technically speaking, the grain, fibers and grain are the same thing, but grain is a more technical term. So they will all be longitudinal, so it means according to this direction. All right? So 90% of the grain that we can take advantage of for structural purposes will be in this direction, the longitudinal direction, and 10% in the other direction. And here you see what I mean. So if we consider a timber board or timber plank, and we draw the three axes, and the longitudinal axis is of course that one, that's the axis that can carry most of the loads. And not too much strength in this direction, and not too much strength in the radial direction. So that's why you need to be mindful of the direction of the fibers or the grain when you're dealing with timber, in particular for structural purposes. If it's about flooring or cladding, it doesn't really matter. It's an aesthetic decision. But for structural purposes, you need to know that the longitudinal direction can carry compression and tension forces equally. And it's strong in that direction. And it's not strong in the other two directions. Now, we also need to make another distinction. So there are, botanically speaking, two types of, oh, someone is marking your assignments on Dropbox. Good. Softwoods and hardwoods. So softwoods related to the conifer types, so the evergreens, and the others are the hardwoods. So what happens is that these are microscopic views of the cellular structures of the two types of timbers. So generally, we can say that the hardwoods tend to grow slowly, and therefore they have a different density. And also, we can say another thing. The softwoods, as you can probably see from this image here, are made of one single cell type, while hardwoods, they have a variety of irregular pores and vessels. So these are more regular. Softwoods are more regular, and hardwoods are not. That's why these are mainly suitable for cladding and flooring, and these are suitable for structural purposes. No, there's always a noise coming from there, but it's not my microphone. No, it's not. I know you're looking at me because you think it's my microphone, but it's coming from here somewhere. And I don't know what that is. Can you hear that? Yeah, it's annoying, isn't it? You should put a complaint in saying that there is a strange noise in class. Now, before moving forward, so you probably already understood that timber has to be harvested, and therefore we need to convert forests into timber products. And last week we mentioned, is cement, we raised the question, is cement a sustainable product, and therefore is concrete a sustainable product? We could say that also timber could potentially be either a sustainable product or a non-sustainable product, depending on the way we harvest our forest, we protect the most ancient forests, and also in the way the chain from the mill until the retailer is actually all the different parts of the process are actually done. In order to make sure that there are certain, that we guarantee there is a minimum standard for the way we do things, there are certifications. 3 main certificates. The first one is Australian, so it's this one, the Australian Forest Certification Scheme, which is defined by Australian Standard 4708. The second one, the Forest Stewardship Council, that's an international certification scheme, which was developed in Germany, and then all the different countries can adopt and develop their own schemes, starting from the basic principles of the international scheme. But what's important for you as customers of timber products and users is the third one, the chain of custody certification, because that will tell you if a product is certified, it will tell you that certain things have been done sustainably, that have been managed properly from the mill to the retailer. So considering that the first scheme is mainly about preserving the first two schemes are mainly about preserving the very ancient forests, there are forests that were deliberately developed for timber products, but they cannot be harvested all at once. So certain areas they have to be assigned each and every year to harvesting in order to make sure that there is an exchange. Otherwise you overdo it 1 year and then you have nothing that has grown the year after. So that's the way the certification works. In terms of timber conversion, now we got to the point that we call the timber logs, the trunks. And there are 2 possible ways to convert them into usable products, such as beams. Back sawing, which is also called plain sawing, just means that you cut the timber longitudinally. And, well, in this way, we just have a tangential cut. We can take advantage of the full length of the trunk, as you can see. So you can take advantage of that. And quarter sawing is instead a little bit different because it's like, you know, slicing a cake. In that case, you cannot take advantage of the full length of the trunk. But at the same time, it's also, most of the times the grain is aesthetically more pleasant. So that's why that can be used for flooring or cladding. And there are a few other things that you need to take into account when deciding to go for either one or the other method. That is, for instance, warping, shrinkage, and other sort of deformations. Right, so in theory, so backsawn timber will generally tend to have a worse grain on the surface, and it will also have problems related to warping or shrinkage. And that doesn't happen with quarter sawn timber. I think you see it better in this slide. So this is the product when it's just cut. And then this is the product after shrinkage. Let's say when that can happen during seasoning, for instance. So if we look at the fibers, the direction of the fibers with quarter sawn, there's a very minimum shrinkage here. And because of the direction of the fibers, with back sawn, you've got this sort of problem. So it shrinks a bit more, but it's also changing shape, you know. And that's why we get into seasoning. Seasoning is a very important process because you cannot use freshly cut timber. What happens is that there is a high amount of moisture inside, you know, the hollow cells of the timber products. So we need to make sure that we lose that moisture to make sure that it's at the same, there is the same amount of moisture between the timber product and the natural environment that surrounds it. Okay? And that is generally between 8 and 15%, depending on where you are. So when you've reached that state, then you can say that it's an equilibrium moisture content and the timber is seasoned. There are two main ways to season timber, as you can see from the slide, and you've probably already seen by reading the time that the product will need to season. What are the disadvantages of air seasoning compared to the advantages of kiln seasoning? But air seasoning, it just means that you take the timber boards, you stack them, and you leave them there for 6 months, 8 months, 9 months, up to 9 months, and eventually they'll season, they'll lose that extra moisture content. You need a lot of space to do that. You also need to wait for a lot of time. That's why kiln seasoning, it's a process that is much faster, so we're talking about something that will happen between 2 and 7 days, and that allows you to control the temperature and humidity within the kiln to make sure that you lose the right amount of moisture in a very short period of time. And of course, true seasoning, but also, you know, since the beginning, since when you start cutting the trees, you can have defects and irregularities, and some of these are very obvious and well known, such as knots, bark pockets. Then it can also warp, it can shrink. You know, these are all the different type of irregularities and defects that timber products have, and unfortunately, they can also develop them throughout their life cycle. And it's not finished, because unfortunately, there are other problems and hazards we need to look at. So mainly, there are two things. The weather is a problem, water, rain. Animals are a problem. In some cases of vandalism, animals can also include humans. But at this stage, we just talk about animals, in particular termites and insects. So termites, what they'll do, they'll just eat your timber products and develop these tunnels. So these are tunnels developed by termites. You won't see them. You need to cut the timber in half, but it will make your product incredibly weak. Imagine that's the joist that's on top of your head. It will suddenly collapse without giving you any notice. So that's why we need to treat timber to make sure the termites won't eat it. All right? We don't want to have those tunnels. There are also a lot of set of other hazards depending on the environment in which the timber is in, and also the sort of application. They are classified using those labels, H1, H2. Like for instance, H3 is what you need for decks. So let's say now that you are in a stage of, you know, between the footing systems and the building frame. So let's pretend you have a deck in your house. You would consider the treatment procedures that you would do for an H3 class. Now, potential exam question. I believe a particularly easy exam question. Let's read it together. Seasoning is a process used to reduce moisture content in freshly cut timber. All right? Which of the following is a side effect of this drying process? Not a defect in general, not an irregularity in general. It strictly depends from seasoning. So which one? Warping, bark pocket, crosswise, internal check. So which one of the four is a direct defect that depends on seasoning? Yeah, that is all right. There is only one possible solution. Generally, it's very obvious. Okay? So we really want to make sure that there is, so the strategy to do multiple choice questions, you probably know that already. One of these four is an incredibly dumb answer. Other two might look realistic, but then if you think for more than 3 seconds, they're just dumb. There's only one realistic answer most of the times, all right? So now that you look at it, just after the slide that, discussed this particular topic, you see how easy it could be to get it right. Okay, we don't do anything that is more difficult than that. We really just need to make sure that you are aware of certain concepts and that you can relate, for instance, 2 different concepts, seasoning and timber defects. Relationship between 2 things, all right? So that's the way, pedagogically, we test knowledge. We need you to identify things and to compare 2 things together. Now, timber treatment, we've already seen the 6 classes before of hazards from H1 to H6. Let's stick to H3, which is about termites for outdoor structures, decking in particular. That means you have products to treat those elements in order for termites not to eat your deck. All right? So I highly recommend you to go follow this link and go through this website. It's an incredible, there's an incredible amount of resources, images, data sheets, anything you want to use for your assignments with proper referencing. But really, there are so many information, there's so much information about products they have, and these are all Australian products that you can find and buy. So I'd really recommend you to insert that into your assignments whenever you have the possibility. Now, there are also very traditional methods to treat timber, which I find fascinating for 2 reasons. First, because they don't involve chemicals. And second, because they give this particularly interesting black color to the final product. So this so-called, I believe it's pronounced Shu Suji Ban, or if there is any Japanese in the room who can pronounce it better, feel free to correct me. But it's really just about burning a Japanese cypress, so the surface is torched, a few millimeters of the surface is torched to make sure that there is this charred finish. So it's literally treated, and it's primarily against sunlight and UV rays. Because you probably know that if you leave timber out there and you don't treat it, you don't paint it, they will just change color. It will become, that sort of gray after a few years. Not many years, 1 or 2 years. So it's very important, for instance, to use a process like this, which I don't know if I'm allowed to say, but it was used, for instance, in the Northcote house for the cladding, something like this, As architects, we really like black as a color. And it's also a traditional method of achieving that color without using chemical, well, in a way you're torching the surface, but, without using chemical products on the surface. Now, another exam question. Let's see if we can answer this one. This is not a multiple choice question. It's a different way, it's a different sort of question that you'll find. So we are providing you 3 statements. One of the 3 statements is false. So we ask you to circle the false statement and then to rephrase it to make it correct. That generally means just changing one word or one verb to make it correct. So what do you think? Do you want me to read them out, or you've already identified the wrong one? Yes? No? Oh, you said yes. Yeah, why don't you try anyway? So what do you think? Well, let's start from the very easy one. Preservative treatments are available to protect the wood from decay and insect attack further. That's good. Timber is dried to reduce its moisture content, and there are two methods. That's fine, under controlled conditions of heat, air circulation, and humidity. That looks all right. It must be number 2. So timber seasoning does not affect the grading, the appearance, and the use of wood members. It does affect the appearance because there will be defects, all right? So in theory, just by changing one word, you can transform the false statement into a true statement. Then if you feel like you are a serious writer, you can change it even further just to make it true, okay? But this is another sort of question you'll find. Now, we're moving from theory to practice very slowly. These are some types of timber, the different species of timber that you'll find for structural applications and for cladding and flooring in Australia. Some of these can be used for both, such as Tasmanian oak, that is used for cladding and flooring, but it can also be used for structural applications. So this is how they look like in terms of color, grain, and for instance, for structural purposes, yellow gum would be the preferred choice. It comes from New South Wales. It's also available in Western Australia, South Australia. And now you might wonder, but why in our case studies we don't have yellow gum? We have radiata pine. We have Oregon. Well, it's a matter of availability, cost, and all those sort of things. You're not always picking the best product for your case studies. It's always a compromise between availability, performance, cost. So in most of your case studies, you'll find radiata pine, because that's the most diffused material. You will also find Douglas fir. Here you go. So this is radiata pine that is, for instance, used to make lintels, all right? So the lintel is that beam that is used when you open a window into a stud wall, and therefore you generate a discontinuity in the structure of the wall. The lintel is able to carry the load from the upper floor and transfer it to the gemstones. Right? So that's the purpose of the lintel, which is made of radiata pine. Now, we have another image here. What we are looking at is timber joists. All right? So these joists are made of Oregon or Douglas fir. And the reason we use Douglas fir is because it's generally available in very long pieces. And most of the times, joists, they need to span, quite a bit of meters. The other thing is that Oregon is incredibly suitable it's really suitable for outdoor applications. So that's why. You can probably see the galvanized plates that are used to make the connection, between the edge of the joists. And now stress grading. Before using a timber product, like it happens for concrete, you probably remember the SLAM test, the compression test. We also want to make sure that we use products that have certain structural properties, You don't want your structures to collapse. So there are two ways to do stress grading in timber. there is visual stress grading and there is machine stress grading or mechanical stress grading. So the first thing that I would ask you to do is to look at the three images. So machine stress grading is what you see there on the right. So this is a timber board. It's supported at both ends. The distance between the two support points is 1 meter. So this is called the 3-point bending test. There is a point load in the middle. We can measure the force applied. And there are 2 support points. We use 1 meter as the span to make sure that we can use it as a unit, as a multiplier. And we just check how far we can go with that bending test. So we can increase the amount of force applied and measure the deformation. So at the same time, we know the deflection that is used to calculate the modulus of elasticity, and we know the amount of force applied to reach that level. If we look at the images on the right, we are mainly seeing defects, knots, all sorts of defects that are assessed by an expert visually. So when the timber products come, there will be someone assessing those sort of defects visually. So they will be graded visually, and an expert person could tell from those sort of defects what's the type of mechanical behavior that the timber is going to have, just by looking at it. So that is the main difference between visual stress grading and machine stress grading. Also, products that are assessed visually are going to be tested using machines. But there is a first selection in which, according to the defects the timber products have, they will be divided into categories. And visual stress grading provides those sort of categories, such as F4, F5, F7. They're color-coded, just to have a simple and fast identification of the grading. F, in this particular case, stands for force. All right. And so that's the source of the Australian standards in which this sort of stress grading is discussed. The Australian standards 1720. And each of these, I haven't mentioned it, but it's in the slide. So F5, for instance, corresponds to a certain force in terms of megapascal. If we move to machine grading, now the acronym is slightly different, so it stands for machine graded pine. And the important thing you need to know that in this case we're actually measuring all the properties of the timber product, in particular the modulus of elasticity. So this is a much better process when you need to make sure that you're using your product for structural applications, so that you will know exactly how much it will perform. It is possible, to a certain degree, to make comparisons between machine grading and visual stress grading. So, for instance, we'll know that an MGP10 would be equivalent to slightly better than an F5, and so forth. All right? Are there any questions so far? Clear? Now, this might be helpful for your assignment because you'll find images in the folders. You will also find them on the websites around. And a product like this will tell you what Australian standards is referring to. That stands for visual stress grading. This is an F5. It was seasoned, thankfully. And it's also a radiata pipe. So it's all in there. You just need to look for the stamp and you'll find the information you need. The same thing happens for machine graded pipe. So again, we've got the producer, the manufacturer, and we've got the MGP tensor grading. So it's generally, there's a stamp on the product that will tell you those sort of things. So we've mentioned the certification, we have mentioned the timber species, the direction of the grain for structural purposes, and the stamp for the stress grading, all right? So these are all important things you need to look at. And at the bottom here of the slide, I don't really want to go through all of them, but I've decided to list you all the different Australia standards that refer to stress grading. So whenever you need that you're going to, whenever you feel that you need to look into those for the completion of the assignments, you have a list, you know, of standards to look at. Now, another exam question. So in this case, it's not a multiple choice. We'll ask you to be a little bit more, to do a little bit more, because you left to write an answer. So it's about a short answer. Identify the name and acronym of the two methods that are used for timber stress grading. 1 point each. So that would be F, visual stress grading, MGP, machine graded fine, and so forth. Now, explain the difference between the two methods. And then you'll have to write a short sentence with the difference. Okay? Very common exam question. In theory, when you answer what's the difference between the two methods, you could also say that it's possible to make, to a certain extent, an equivalence between the two. You could mention that an F5 would be more or less like an MGP10, and so forth. So you could, the more you add, the better. Now, what we've seen so far were all natural products, so we're just natural timber products. We also have plenty of composite products. And the way to look at this diagram is that you start from the timber logs, and there will be three main families of composite products, starting from timber boards, from veneers, and strands. So from timber boards, you, for instance, would get the glue laminated timber, or glue lam, CLT. All right? You probably have seen glue lam, or you've heard that before. Veneers, from the veneer, you get the plywood, and you also get the LVL, which is the laminated veneer lumber. And from the strands, you get the oriented strand board, and a few other products. You'll see why I'm mentioning this in a moment. But before that, just a curiosity. This is an ancient, an ancient application or experiment to develop a composite timber product. So this is Philippe Delors. We are in the 16th century. There is no glue, of course, because glue lam means that there are two boards which are glued together. To do what? To make a longer element and a stronger element. So in this case, there are two timber boards which are connected with those key elements that they're literally working like nails. And the overall idea was to make an arch with a very long piece of timber that could be considered nowadays as a composite product. But that was really just the beginning to develop what we now know as, for instance, LVL, or the I-beams, which are made of two different elements. So, for instance, the top part, the top chord and the bottom chord are made of LVL, and OSB is used to do the web. I think that in both of your case studies, you've got the parallel chord trusses I believe that's your case. So again, we're talking about top and bottom chords which are made of LVL. And what they're called here, the web struts, so those guys in diagonal, they're not really struts. I would call them bars, because strut means that the element is in compression. They're not necessarily working in compression. So bars, structurally speaking, means that these are elements that can either work in compression or tension within a truss system, but we don't know which is the case. Okay? So some of these will work in tension, some in compression. So you can call them struts, but it's not structurally accurate all the time. So in a truss system, it's just better to call all the elements bars. So when there is no deflection and there is only axial forces, we're talking about bars. Other interesting products, glue laminated timber. So that is just simply a number of laminations, face bonded and finger jointed together with adhesives. So there is glue. And cross laminated timber, I think it's the same thing with planks, but the difference is that the elements are glued, the layers are alternated in terms of grain direction. So cross-laminated timber, it's particularly important for structural purposes. It's a very recent product. It was developed in the 70s, and if you consider, normal plywood as the material that you would use at the fab lab of the MSD to do models, let's say, for instance, to do the base of your models, this could be called, this is actually called jumbo plywood. To me, it's a very strong product. There are always an odd number of layers. So that means that the first and the last layers have always got the same direction of the grain. Because let's say you're going to use that in this direction as a beam. You want to have the outer layers sharing the same direction of the grain. The same if you flip it and you rotate it vertically and you use it as a wall, you want to have the same direction of the grains. All right? I hope that's clear enough. If that's not clear, let me know. But just make sure, odd number of layers. When you look at it from both sides, the grain has to run in the same direction. Important characteristics of cross-laminated timber. You can actually make tall buildings out of it, up to 12 stories, as far as I know. So that means that this could replace steel and concrete entirely. It can be digitally fabricated, so there are a few advantages of using cross-laminated timber. And as you can probably see from this slide, it's still the applications, serious applications of cross-laminated timber are still experimental. So we're not talking about something that is standard and used everywhere in construction sites. All right? We're talking about very specific and most of the times expensive applications. And exam question, I think that's a little bit difficult. List and explain 2 characteristics of cross-laminated timber. 3 marks each because it's a bit more complicated. So what are the important characteristics of cross-laminated timber? There are more than 2. If you really had to select 2. Well, that is not a characteristic. I know what you mean. That is more of an intrinsic property of the way the system works. Characteristic, it could be related to the way it appears, it behaves structurally, the way it's manufactured. So it could be any of those. So what did you have in mind? Yeah, so that is a characteristic of CLT, that it's a much stronger material than just natural timber. But then you would need to explain why, because it's a composite of this, and that. For instance, the sort of answers I had in mind was that it could be digitally fabricated because of the way of the alternated layers of timber, which are glued together. So that was a possible answer. The other answer is that it could be used for structural applications, but serious structural applications like up to 12 stories. So when I say characteristic, I mean something that cannot be found in another timber products. So it's something that really identifies that particular product. All right? So being suitable for structural applications, it could be common to any timber products. But being suitable to build literally a tower or a skyscraper is only a characteristic of cross-laminated timber. And also the capability of being digitally fabricated is only related to these and some other composite products. So when I say characteristic, I know it might sound generic, but I think it's good that you've raised the point, because we are really talking about what identifies that particular product and not any timber product in general, all right? Is that okay? Is that answering your question? Any other doubts about an exam questions like this? All right, I'll give you a 10-minute break. You're particularly silent today. Do you have a submission for Studio Gamma or Environmental Building System? Or am I just too slow? Because yesterday was the open day, so I'm also a little bit deflated. Or it's a combination of the two. Maybe we're both tired because we both had a submission. But we'll see you back in 10 minutes. So we'll meet at 22 past. Right, very well. Let's start again. So what do you see in this slide? What's that? Come on, this is easy. No, it's not so obvious because nobody is responding. Anyway, that's the balloon framing, yes. That's what I wanted you to respond. Because we're going to have a look quickly in 3 slides at the history and evolution of timber construction in terms of framed construction. So it all started with this sort of constructions in which the joints and all the carpentry was done manually, so there was not standardization. That's a very complicated joint that requires craftsmanship, and the elements were heavy. So that's why we talk about heavy timber frame construction. And we moved extremely quickly to the 19th century, in which we developed the balloon frame system. So why did that happen? For 2 main reasons. The first is the invention of the circular saw that allowed the development of these timber products, slender and light timber products, which became inexpensive and readily available. So that's why we moved from heavy frame construction to light frame construction. And the second very important advantage is the invention, not of the nails, because the Romans used to have nails in the past. I'm talking about the common industrial nails that can be produced in hundreds and thousands easily, cheaply, all right? And screws, which are even better because you can place a screw and also remove it without damaging the timber product. And that wouldn't happen with nails. So the 2 inventions, nails and circular saw, defined the so-called light framing construction. If we go back, we see something that was particularly noticeable in the slide that I put up during the break, which is the fact that the studs are actually running through the entire height of the building, from the ground level until the roof. And then the floor joists are connected to the studs. So you can already foresee that there are a couple of issues here. The first one is about safety in preparing and handling those very long elements. And the other one is about being able to transport long elements on site. It's quite different when we move to balloon framing. To platform framing. I think today I'm really tired. But anyway, that happens. Platform frame. So the difference is is very important and obvious. So the studs were breaking down into two parts, ground floor and first floor. So the two advantages are shorter products to handle, below 3 meters, very easy to transport, very easy to place, they're safer. And there is another advantage. You don't really need a scaffold if you're working at the ground level. And once the ground level and the first floor is completed, you can actually work on it to develop the second floor. So this is an evolution of the original balloon framing patent. All right? So, but I think it's important that we need to know that we're coming from heavy timber framing, and then we move to light timber framing, what you see sometimes in old movies, American movies, and then to platform frame. So the platform frame is what's commonly done here in Victoria. You'll see it in your case studies. You'll see it in this picture, for instance. You can recognize it because the joists, in this case posi struts, are here, and the studs of the ground floor and the first floor are there. You'll see in this slide something else, a lintel there, strap bracing, steel strap bracing. And the terminology is in the Australian standards I mentioned before, 1684.4. That is going to be your Bible for the next weeks. Nothing else. You won't be allowed to read anything else than that. So if we now consider this terminology that you probably know already from year one, we can look at all of these elements one by one, starting from the ground level. So let's look, for instance, at the stumps, the bearers and the false joist, and we'll also look at the hand cap. So this is how it looks like. So a decking system, this is the sort of detail in which you have the stumps, the hand cap, to make sure that termites and other elements won't be able to climb. The bearers and the joists running in the orthogonal direction, they're supposed to be treated to make sure that termites don't eat the timber and create tunnels. That is the sort of connection that you could do should you need to extend the length of a bearer member or of the joist member. And then when we move to the wall elements, which are particularly important for you for stages 3 and 4, in some cases even stage 5, well, I think I'm mentioning very basic things here. Studs, bottom plate and top plate, which correspond to these elements respectively, bottom plate, top plate. What else? Noggins are here. Bracing. In this case, we're talking about steel bracing. Now the lintel, which I already mentioned before, and the jam studs. So these two elements together allow you to create an opening in the stud wall, but by doing that, by puncturing the wall, you're creating a discontinuity, and therefore you need to make sure that the forces that are coming from the first floor are somehow transferred in another way. So the lintel is transferring those forces to the jam studs and to the ground. In a site visit that we did last year, I think we were able to see most of these elements, such as the lintel there, the jam studs. All right, this was Peter, one of our tutors. Now, noggins and bottom plates. What's the real important role of noggins? The fact is that the studs are incredibly slender, and there is a structural property you need to consider, which is buckling. When you have structurally slender elements, they always tend to buckle, and they tend to buckle because of their height and the slenderness. But if we insert, if we reduce the height of a slender elements by half, because we insert a knocking in between, then we reduced or even neutralize buckling entirely. So these images are taken from that Australian standard, the 1684.4, which tells you the spacing between studs, which tells you at what height you need to place the knockings. So everything is in there. You don't have to guess anything. It's all given by the standards, all right? The way it looks like is this. All right, so more or less they are placed in the mid-region of the wall. But there is also another thing that you need to notice. They are not aligned. So why aren't they aligned? Because you wouldn't be able to, to drive the screw of the nail to place. So that's the reason why they're not aligned. It's not really important they are aligned for structural purposes. They only need to reduce the height of the studs. So that doesn't really matter. But you need to be able to place them easily. So that's why you've got that shape. And now bracing. I believe that's another concept that is a concept that you're familiar with. So do you all know what bracing is and why do we need to brace a structure? Yes? All right, let's have a look at this structure here. This is a structure made of 4 elements, which generates a quadrilateral structure. And this is a triangular structure. This one is structurally stable, and the other one is not, because it can move in that direction. So it can be deployed, it can be folded. By adding a diagonal element, we make sure that that folding doesn't happen. All right? So we always need to transform quads into triangles. That's the basic rule, let's say. And stud walls don't really have diagonal elements unless we introduce them through bracing. So bracing can be done using temporary props while the elements are put in place. And there can be permanent steel straps to keep the structure in position and braced at the end. There is also another possibility, which is sheet bracing, this one here. So in that case, you've got a panel, a ply panel, and that will also work in terms of bracing. So we've also seen most of these things on site. And the interesting thing, when you go to visit a construction site, being able to see things in 3D, you realize that bracing is not strictly related to a wall. It's also related to lateral stability. So it's about this wall here, but also the wall in the orthogonal direction. And also it's about the flooring system that's on top of my head. So it's also about that system. So those joists, those trusses actually, they need to be braced in that direction. So while you're going to draw the plans in your flipbook section, perhaps we're talking already about stage 5 and 6, make sure that you consider the bracing system that's added to that part. If you draw a stud wall and you see the stud wall in section here, but in elevation, in the background, you see there is another stud wall, perhaps that's also braced. So make sure that in your flipbook section assignments, you always represent what you see in section, but also what's visible in the background, all right? So make sure that you consider the way the building works in 3 dimensions. What else? So here you see a particular way of steel bracing. So this is done with only one single strap. So it means that the top plate is connected to the studs with this single strap, which then folds, as you see here. So, and the two connections are there. Here is what the standard says. It has to be done at 30 degrees to 60 degrees. So here's the connection. You also see a gas pipe. I don't really know why we have highlighted that, but now I think this is more important than what you've seen in the slide before, because it allows you to see two different ways to do the same detail. So one is having a single element like that. So that's the steel brace that connects the stud to the top plate. So there's one single element. And then this is another possibility. It's a much stronger connection with two elements. So first you've got a tie that connects the top plate to the stud. And then there is the steel brace, the strap, which is a separate element, all right? And this is how it looks like. So in this case, it's a much stronger connection, because there is this tie first, and then the second one there. Now, there are a few other things related mainly to internal partitions, which you're probably going to see already at this stage in most of the cases. And you want to make sure that you know how the corners and the intersections, you know, with a wall and an orthogonal wall, how they were handled in your particular case study. So these are possibilities for T-junctions and corners. There are generally 2 to 3 options for each of these, and you want to make sure you use the one, you become familiar with the one that was used in your case study. Upper floor framing. Well, we've already seen before the joists up there. I don't think you're going to use those joists in your case study. In the case you need to open a skylight or you have stairs, then you need those trimmers that restore the discontinuity you've generated by cutting the joist. This is a typical floor joist connection with galvanized plate. And the posi struts. All right, this is the sort of connections that I believe some of you have in the case study. And this is how the students in the past communicated to us how the house was built using hand drawings, such as in this case. And I think it was a very effective way of doing it, even if, you know, not particularly accurate in terms of drawings, but very effective in terms of communication. I think also the use of colors, if it's well done, it can help understand certain things. So you see all the components of the stud wall are there, including bracing. In that case, there was even a steel structure, temporary works, tools, equipment. You see some photos and details of connections, and we're mostly talking about the connections I've just mentioned. I just didn't mention the connection between the bottom cord, but the bottom plate and the concrete slab. But you know, you really want to focus on the connections between vertical and horizontal elements. You want to focus on the connections between the different parts of the same building system. And you want to have a combination of photos, sketches, diagrams, which can be in plan, section, perspective, axonometric view, whatever you might find appropriate to describe a particular concept. And of course, we also want to know the details, you know. We want to know what material is that, the dimensions, if they are available. And moving on to the first floor, you see that there is a scaffold coming. There are some extra connections. And this is a different assignment, organized in a completely different way, but talking about the same thing. What I like of this assignment is the way the page was organized. Like the flipbook section is always in the middle, and photos are always on one side, and the details and other things are always on the right side. It makes it incredibly legible. You know, if you just flip through the slides quickly, it's incredibly easy to understand. So I particularly like when photos and details don't overlap with the drawings, which can become a little bit more confusing. But, you know, there are different techniques and they all work in different ways. So we see all the elements are there as well, including temporary props, equipment, tools, workers, the connections. The most important connections are always highlighted, some pictures relevant to that stage. Moving to the development of the first floor, the posistrat, it's there. Most of the connections are also drawn, and scaffold, temporary props, you know, it's all there. First floor, lintel to double stud detail, some images, and another example. In this case, the student has decided to, you know, highlight a few portions of the flipbook section to describe what's happening in those areas. That's also another effective way, you know, to highlight things and to bring attention to some parts of the assignment. Moving to the first floor, again we'll see the posistrats, and most of the times we see a detail of an opening or how the posistrat is made, connections between orthogonal elements. And then roof framing. So roof framing, which just means we're moving one level up, we're still talking about the same elements. So there will be studs, noggins. Just in this case, the connections will be slightly different because the rafters are going to be inclined in most of the cases, all right? So the roof truss connections, which are probably not relevant for you this week, but will become next week. But consider we're going to talk about steel next week. We'll have to discuss them today. You'll find in these slides most of the connections that will apply to your case studies. You've all got pitched roofs, and therefore these are the sort of connections you want to look at. Some other photos with straps, bolted connections, galvanized plates. Now, I'd just like to focus on one thing before you go. I don't think it's important to look at all of those details because you all have different situations considering your section cuts are different. So those slides are just there for you to look at and discuss them with your tutors. I think we mainly need to discuss the principles here. So what happens when you have stairs and skylights? You'll need to puncture the floor structure. and generate a discontinuity. We'll see in a minute what that means. But I thought it could be helpful, particularly for the students who have been so unlucky to get a cross-section through the stairs. So I thought it would be at least fair to show you a couple of slides about, let's say, a traditional stair made with timber elements. There can be very similar details just using steel components, at least for the stringers. So those could be replaced with steel elements easily. So this is the terminology. The stringers are the structural beams that connect the ground floor to the first floor. Then there are the treads. So they are the footways. It's where you step on. The risers. So those vertical boards are the risers. All right, so that's what you need to know. And this is how, assuming you've got posi struts, you generally use a header beam like this one to restore the continuity, the structural continuity that you've interrupted by generating this opening. So the load that is transferred by this beam is transferred to the other two posi struts, and you're going to be fine. So let's say you are in a situation like this. This is not your case study. It's a house from years ago. It's an old case study. So the way I would do the assignment at this stage, I would try to understand what happened structurally first, because that's the first thing you need to look at. So if the building can stand, and if you can add protections and cladding and finishes, it's because there is a structure that is standing. So by combining images and plans and sketches, you're generally able to do that. In that case, we've got a steel frame. So we need to understand the direction and position of the main structural elements. So these are the main structural steel elements. And then I realized that the joists are running in this direction. So that means that if the stair is placed here, it's actually a very difficult scenario, because if the stair was oriented by 90 degrees, I could have just got rid of a couple of joists, and that was it. In this case, it's a bit more complicated, because I need to make sure that I have a trimmer, and I make sure that those two joists are a little bit stronger to make sure that the structural continuity is restored. But this is more or less what you need to look at when you meet a skylight or a stair. So the first thing you want to look at is the direction of the joists. If the opening is running along the direction of the joists, you're lucky. If it's not particularly complicated, but it just means that you've got a couple of extra elements that are used to restore the structural continuity of the floor structure. All right? So I believe that for today we are done. And there will be steel next week. Unless there are any particular questions about timber and the assignment that you'd like to ask today. I knew that. Anyway, there is a question. Sorry, I can't hear you. Yes? So you're saying that your section is very wide and it cannot fit in on the page? Right, so you've got two walls, two external walls, and you want to cut it in the middle. That is possible, but what I would suggest is that you only focus on one of the two external walls and cut the section towards the end. I wouldn't cut it in the middle, so I would just discard one of the two external walls, but don't interrupt it in the middle. Okay? Any other questions? Complaints? No? All right, so I'll see you all next week or maybe tomorrow around the tutorials.